Well, I sent the correct practice test about 15 minutes ago. So I'm certain you've all had enough time to work on it and get it all straightened out. So that's good. I sent the wrong practice test in an email last week thinking that, well, at least they got something to work on. Well, that was useless to you. So don't watch this video until you've tried the practice test, because these are the answers to the practice test. Here we go. Here's the first bit. Let me get that camera a little bit more head on. Let's make it look straight up and down. Just going to get this to look good. There, you can sort of read it. There we go. Okay, so the first problem, it's a fairly simple system, not even a squared. We do have a little product there, but that's about it. And we're supposed to check to see if it's Hamiltonian or gradient. So I took the partial of the first function with respect to x, and I got negative sine x. And then I took the partial of the second function with respect to y, threw an extra minus sign on it, and they match. So it's got to be Hamiltonian. So that's good. And now to do Hamiltonian, I got to take the first differential equation and do the antiderivative with respect to y, but add on a pure x term as an option in case I need it. And then take the second function and do the antiderivative with respect to x. Don't forget the extra minus sign, because they match by an extra minus sign, so I have to throw the extra minus sign in there to get these guys to match down here. So if you do it right, if you do it with the right stuff, everything should work out okay. There's two terms here, but only one term here. So there's probably going to be either a pure x or a pure y term. There's got to be something left over. So when I do the antiderivatives of each, I get a 3y squared from the first one that isn't in the second. So if you notice, I did these two integrals, and then I wrote these two answers, so they correspond, like, you know, the first one, the second one, the second one. So the actual Hamiltonian has to have that 3y squared in it, and it has to have a y cosine x. You can take partials of this and make sure you get this back, but remember, you're going to be off by a minus sign for that second one. So that's that one. Number two is right there. We've got almost all of it on screen here. Let me see if I can get the rest of it on there. Yeah, because I'm starting up number 3 down there. Okay, so number 2, another system. This time you kind of expect it to be gradient because the first one was Hamiltonian. So I did the gradient test first, which is I take the partial of the first equation with respect to y this time, and the partial of the second equation with respect to x, and they match. They're both 2y. So that means that I do the first integral dx, and the second integral for the second equation I do dy. And those guys got to match up along with the options of a pure x and a pure y. And in this case, I have a pure x and a pure y. I just did this because, by the way, each of these integrals, each of these equations has two terms. But there's a pure x term and a pure y term. So I'm going to have a pure x and a pure y term in my final function. So they both have xy squared in common, but then I've got to have a minus sine x and a minus cosine y. And then you can check by taking the partial of this function g with respect to x, and it'll match little f. And I can take that partial with respect to y, and it's going to match little g, the second differential equation. So there's that. Number 3, let's see, number 3, and number 3 fits right here. There's not too much to do. Here's a very small picture of what's going on. You want that first quadrant. That first quadrant's only going to have a couple of nullclines in it, and they meet here at 1, 1. So let me see. I'm going to have arrows around it that look like this. This guy's going up. This guy's going across, this guy's going down, and this guy's going across that way. So there's two equilibrium, one at the origin and one here. and they ask for the Jacobian of that point. Well, you got to do the math to get that point. So that's what these notes are off to the side. I'm putting the two equations together, substituting one equation into the other, and solving for y. I get 2y equals y to the fourth over 4. I can divide by y and multiply by 4, and I get y cubed equals 8, which is very good news. That means y equals 2. And for either of these equations, x equals 2. So this point is 2, 2, and they wanted the Jacobian at the non-origin equilibrium point. This is the only other equilibrium is 2, 2. So I took the Jacobian, there's my partials, and then I put in the 2, 2, and I get this. Now this is just an FYI off to the side. This is all that was requested, the Jacobian at 2, 2. Notice there's no 0 entries. I did the formula for finding the eigenvalues. And it turns out this one has pure imaginary eigenvalues, which looks good because if you notice, I've definitely got some kind of loopy pattern around here. It could easily be the case that I could have a circular solution curve if I needed to. You know, I could have a solution curve that's round if I had to. So there's a good picture of null clines for you. And nobody asked, but that's what the solutions are doing near that equilibrium. They're either circles or ellipses. Shouldn't be a spiral because I've got the pure imaginary. But that's not a question that I'd give you unless I gave you the actual eigenvalues and then ask you about what's the stuff. Because remember, there's no zeros for any of the entries, so your shortcut page doesn't work. Okay, going on to number 4. Number 4, please ignore. Here, I'll cover it up with this. I got a better picture coming up of the null clines. So there's number 4, number 4, number 4. Let's get it straight across. Number 4. Okay, so there's the differential equations, and you have 2 prints of the direction field that go with it. And they asked, where's the spiral at? And if you notice, there's really only one candidate for it. It has to be at 0, 1. When we see the full set of null clines here, you can see what's going on. Here's the full set of null clines. When you look on the actual page, this equilibrium has some interesting stuff going on, but it's above y equals 1. This guy has to be the spiral when you look, because there's this loopy thing. There's this loopy thing, and then there's an equilibrium above it. So this equilibrium has to be the one that gets the spiral when you look at the direction field. So here's the null clines in black and the arrows on the null clines in red. I've marked the equilibrium points, which were not requested, which is good because some of them would take a little bit of work to find. Most of them are pretty easy. Like this guy is at y equals 1 and x equals 0. So what you got is you've got horizontal null clines when dy dt is 0, and you got vertical null clines when dx dt is 0. So you write those in. There's a nice little coincidence here because this piece of null cline should be getting a horizontal arrow as well as this piece, and it's both the same kind of horizontal arrow, confirming that they fit the direction field. You've got it pretty good. So something like this is very easy to do because you've got the direction field. You can draw right on it and get the pieces. Now, the hassle is I'm going to remember that some of you might not have a good printer at home. So, if you have to copy it over by hand, it's cool if it looks a little jaggy, if it looks a little junky. I know you're doing it by hand. All right, 5th problem, last one. All right, so this was a given formula, and they wanted you to make a system that's going to be Hamiltonian with this as its solution. So all you got to do is take the first partial with respect to first partial with respect to y, second with respect to h, x with respect to x, and don't forget that extra minus sign. So this is your system. You don't need those h's in between. You just have dx dt equals this, dy dt equals this. Guarantees that will be the Hamiltonian surface, if you took these and did the antiderivatives, if you did the integrals. But there's no reason you don't have to do that if you took your partials correct. And there it is, your answers in under 10 minutes. Sorry, there's no ferret. Maybe next time.